Collaborative Filtering Part B. Now let's understand how item-based nearest neighbor works. Item-based approach is preferable to user-based approach. So what is the reason behind this preference? Because of the dynamic nature of users, user-based approach is often harder to scale as the items usually don't change much. Item-based approach often can be computed offline and served without constant retraining. KNN is the perfect go-to model to implement an item-based collaborative filtering. It is also a very good baseline for recommender system development. Look at the given example. In item-based collaborative filtering, you need to look for items that are like item 5 and then take Alice's ratings for these items to predict the rating for item 5. The choice of the K nearest neighbors for the neighborhood formation results in a trade-off. When you use a very small K, only a few candidate items can be recommended because there are not a lot of neighbors to support the predictions. While the particularities of users' preferences can be blunted due to the large neighborhood size, so a very large K impacts precision. The optimum K also depends on data characteristics such as sparsity. So K is set to be in the range of values from 10 to 100. The similarity is measured based on two algorithms, cosine and adjusted cosine. Cosine similarly has better impact in item-to-item filtering. Here, ratings are seen as a vector in n-dimensional space, so the angle between the vectors is used to calculate the cosine similarity, whereas adjusted cosine similarity takes average user ratings into account and transform the original ratings. Association rule mining. At a basic level, association rule mining involves the use of machine learning models to analyze data for patterns or co-occurrence in a database. It follows association rules, which is to identify frequent if-then associations. Given a database of transactions, each transaction is considered as a list of items. It finds all the rules that correlate the presence of one set of items with that of another set of items. It identifies the frequent patterns. It is most commonly used for market basket analysis. Association rules are created by searching data for frequent if-then patterns, using the criteria support, identifying the most important relationships. Support is an indication of how frequently the items appear in the data. It provides a fraction of transactions containing the item X and Y. Support is calculated as the number of times item X occurred divided by the number of transactions. Confidence indicates the number of times the if-then statements are found true. It indicates how often the item X and Y occur together, given the number of times X occurs. It is calculated as the number of times items X and Y occurred divided by the total occurrence of X. A third metric called lift can be used to compare actual confidence with the expected confidence. It indicates the strength of a rule over the random co-occurrence of X and Y. It is calculated as the number of times in X and Y occurred divided by total occurrence of X multiplied by total occurrence of Y. Association rule mining, market basket analysis. Let's understand the association rule using the given example. Market basket analysis is a modeling technique based upon the theory that if you buy a certain group of items, you are more or less likely to buy another group of items. And item set is the set of items that a customer buys, and market basket analysis is used to find the relationships between purchases. Here in the given example, A, B, C, D, and E are items in a store. P is the set of all transactions that are P1, P2, P3, P4, P5. So you can see that each transaction is a set of items. Consider you made some association rules using the given transaction database. Support is a measure of how much the historical data supports rules defined and confidence mean. Confidence mean is the measure of how confident we are that the defined rule holds true. Support can be calculated as the fraction of rows containing both A and C or joint probability of B and C. Among the rows containing A, confidence is the fraction of rows containing D or conditional probability of B given C. This is the ratio of confidence to support. If the lift is less than 1, then A and D are negatively correlated, else positively correlated. If it is equal to 1, it is not correlated. So when you are calculating support, confidence, and lift, values will result in the given matrix. Association rule generation, a priori algorithm. Candidate item sets with the a priori algorithm are created using only the large item sets of the previous pass. The large item set of the previous pass is joined with itself to generate all item sets with a size that's larger by 1. Each generated item set with a subset that is not large is then deleted. The remaining item sets are the candidates. It uses frequent item set to generate association rules. Frequent item set is a set of items whose support value is greater than the threshold value. With this approach, the algorithm reduces the number of candidates being considered by only exploring the item sets whose support count is greater than the minimum support count. A priori algorithm example part A. The number of item sets that have to be examined can be pruned using the a priori principle. The list of popular item sets can also be obtained. We have the given data of a store. Scan the transaction database to get the support S each one item set. Compare S with min sup and get support for one item sets. Let's assume the support value is. Create the item of the size of 1. Calculate their support values. As you can see here, item 4 has a support value of 1, which is less than the main support value, so we are going to discard 4 in the upcoming iterations. We have the final table, F1. Start with item sets containing just a single item. Determine the support for the item sets. Remove the item sets that do not meet your minimum support threshold, and keep the item sets that meet it. Use join to generate a set of candidate K item sets. Use a priori property to protect the unfrequented K item sets from this set. Next, create item sets of size 2 and calculate their support values. All the combinations of items set in F1 are used in this iteration. Item sets that have support less than 2 are eliminated again, in this case 1, 2. The length of an item set is extended. All the combinations of item sets in F12 are used in new candidate key C3. Now let's understand what is pruning and how it makes a priori one of the best algorithms for finding frequent item sets. Using pruning, we are going to divide the item sets in C3 into subsets and eliminate the subsets that have a support value less than 2. A priori algorithm.